All right, subscribers, welcome back to another episode of Science with Surback. Today what we're going to be talking about is sections 5.6 and 5.7, which deals with Hess's Law and our standard enthalpy of formation calculations in AP Chemistry. Now, before we get into the details of these notes, there's a few objectives that I would like you to be able to accomplish by the end of this video. So objective number 1. State Hess's law and apply it to calculate the enthalpy change in a process given the enthalpy changes in other processes that could be combined to yield the reaction of interest. Objective number 2, define and illustrate what is meant by the terms standard state and identify the standard state for elements carbon, hydrogen, and oxygen. Objective number 3, define the term standard heat of formation and identify the type of chemical reaction with which it is associated with. And objective number 4, calculate the enthalpy change in a reaction occurring at constant pressure given the standard enthalpies of formation of each reactant and product. So we start out here with Hess's law. And Hess's law states that if a reaction is carried out in a series of steps, the change in enthalpy, or delta H for the reaction, is the sum of each of those changes of enthalpies, or delta H's, for each step. And the reason we can do this is because we have delta H as a state function. And so just as a brief reminder, a state function means it doesn't matter the path that we took to get to the end state. And so we'll learn here in just a second the steps with Hess's law, but I'm going to put this, and I may put it multiple times throughout these notes, for Hess's law, and really for standard enthalpies of formation, which we'll get to at the end, states of matter matter. And that is going to be a key thing that we need to keep in mind throughout this entire process. So let's turn to the steps of how specifically we can use Hess's law. All right, so what we need to do here is we need to determine the desired chemical equation. Now, this will be given, okay? So you're never going to have to come out of the blue and find the desired chemical equation. It is given, and I'll show you where it will be given. But then we're going to be giving a series of reactions that are possible to be able to get to this desired chemical equation, and we're going to have to manipulate them, multiply, divide, flip around to get to what we want. And remember, when we multiply, divide, or we flip the reactants and products, we also have to do something to our delta H value for that reaction. And then at the end of the day, we're just going to add those given equations together to get to what we want. It's kind of a double check, and then we add our delta H's, or our changes of enthalpy, with this. Now, the reason that we have to use Hess's law is that it is often difficult to calculate the energy changes directly for many reactions. And so the real reason we have Hess's law is kind of an extension here. Other reactions can be calculated in terms of delta H, and when we add those together, we can determine the change of enthalpy, or delta H, of the desired chemical reaction. All right, so the steps can only do so much. What's best to do here is actually apply these steps to see these in action. Once you see that, it'll be a little bit more familiar, and some things can be a little bit easier. So let's go ahead, let's try an example of Hess's law. Now we're going to start real simple here, and it says calculate the delta H, or change of enthalpy, for the following reaction. We have solid carbon plus our half oxygen yields carbon monoxide, which is a gas. And what this is here, this is our desired equation, okay? So this is our desired equation. And like I said, you're never going to have to just come out of the blue and find this. It will be given like this. Now here are some considerations that we have to think about that could be possible solutions to be able to produce this reactions, and respectively could add up to equal the delta H's we desire. So how I view this is as follows. I look for something in our desired equation that is found in our first equation given. So I look here, and in my desired equation, I want carbon on the left-hand side, and I want one of them, okay? So I go down here, I find carbon, it's on the left-hand side, and I want one of them. I don't need to manipulate or change around anything. So what I'm going to do, I'm going to recopy this down here. So I'm going to have solid carbon plus our oxygen gas yielding CO2 gas. And that gave me a delta H of negative 393.5 kilojoules, okay? And now what I'm going to do here is this. Whenever I rewrite something, I'm going to cross it out so I don't reuse that up above, okay? Now, I'm going to go down here and I'm going to look in my desired equation, and I see that I need carbon monoxide, CO, on the right-hand side. So I look here, and this equation here has CO, and it's on the left-hand side. So remember from our rules on thermochemical equations, we can flip this equation, and so we could have CO2 as a gas. We could have CO2 as a gas, yield carbon monoxide as a gas, plus our half O2. Now, remember from our thermochemical equations here that these things flip. And I should say this is a gas. If you want to add that in there, just so you know, that is a gas. It should have been written in there. But what happens here is this. When you flip the equation, you have to flip the sign of delta H. So our delta H is now positive 283. So we flip the equation, we flip the sign for delta H. Now what we're going to do, we're going to leave those delta H's alone, and we're going to do some canceling. Okay, so I'm going to make this general statement. I'll pause and then I'll write it down. And we can cancel elements or compounds on opposite sides of different equations. Okay, so we'll get to that here in a second. But again, I wrote this out. And so whenever I do that, I always cross this out so I don't confuse those particular numbers. All right. Now, let's get to this statement here. Elements or compounds can cancel if they're on opposite sides of different equations. So check this out. CO2 in my top equation is a product, and CO2 in my bottom equation is a reactant. So when we go to add these together, these would cancel out. All right? So we would no longer have CO2 to worry about because 1 cancels with 1. And then we turn to this. We have O2. They're on opposite sides of the equation, but we only have half of an O2 and we have 1. So what we do, 1 gets canceled out with half here, so we eliminate this, and we no longer have 1, we have half, okay? Now, to solve our equation, all we're going to do is we're going to add all of these equations together, and we'll worry about delta H here in a second. So I have carbon that's solid. We look for carbon that's a solid. Can't find anything else, so we just put carbon as a solid. And then we have half O2. Remember, we have canceled that O2, so the half O2 is written down as such. Now everything else on the reactant side on both equations is canceled, and so what we can do is So we can draw that reaction arrow. And there's only one thing left on the product side, which is CO gas. Okay? Now, we ask ourselves, does this equation match what we have here? So we have solid carbon plus half O2 yields carbon monoxide. Hey, that's a verified exact match. So what this says is, because we manipulated it in the way we wanted, these given equations, all we need to do is add these delta H values together. So all we're going to do is take negative 393.5 times, plus 283.0. I press enter, and so the delta H for this particular reaction is negative 110.5 kilojoules. So the delta H for this reaction is negative 110.5 kilojoules. All right, so that was a pretty straightforward problem because we only had two equations we had to manipulate. What if we go a little bit further and we have three equations that we have to manipulate? Okay, so this problem here, it says, hey, calculate the delta H or change of enthalpy for this equation. And again, this is our desired equation, okay? And we have these reactions here, okay? So again, the first thing that I look for is this. I look at the first equation and I try to find something that matches up here. Well, check this out. I need C2H2 as a gas, and this first problem has C2H2. However, it's on the wrong side. Now I still only need one of those C2H2s, so all I have to do is flip the equation. So now I'd have 2CO2 as a gas plus H2O as a liquid yields C2H2 as a gas and 5/2 of O2. Now again, I flipped my equation, which means I need to change or flip the sign. So no longer is it negative 1,299.6, it is positive 1,299.6 kilojoules. And I go and I do the same thing, okay? So on this equation, I notice here, hey, I need carbon on my left-hand side, but I need two of them. This one has it on the left-hand side, but it only has one of them. So remember, what we can manipulate with our equations to make this carbon a 2 is we multiply everything by 2. So we're going to have 2 carbons that are solid plus 2 oxygen gases that, again, are gases, and we have 2 carbon dioxide, CO2s. Now, because we multiplied everything by 2, what that means is our delta H has to be multiplied by 2. So we're going to take negative 393.5 times 2, and that's going to be our new value for delta H. So our delta H here is going to be 787.0 kilojoules. Okay? And now the last thing that we need here is H2. All right? H2 is on the left. We need one of them. Check this out. H2 is on the left. We need one of them. So again, I rewrite this as H2 as a gas plus our half O2 as a gas yields our H2O as a liquid. Now, we did not manipulate, we did not change or reverse or double or divide. So that means our delta H is going to stay exactly the same at negative 285.8 kilojoules. Now, what I like to do and what I did on the previous problem is once I've rewritten them, I cross these things out. So that way I don't interfere and I don't mess up what I've written. Now, key thing, I'm not going to write this down again, but key thing, elements or compounds that are the same on opposite sides of the equation can cancel. So we're looking for similar things on opposite sides of the equation. First thing that pops out here is H2O. H2O is a liquid on the reactant side of the first, and the last, it's a product. So these guys, because they're both 1 and 1, can cancel out. Now, I keep looking for things that can also cancel out, and check out carbon dioxide. Carbon dioxide, there's 2 of them. On the opposite side of this middle equation, there's 2 of them. So because they're the same thing on opposite sides, you cross them out. And we keep looking for other things that we can cancel. So we have to be careful here because of this. If you do 2 plus a half, you get this in the calculator. Now, what may help here is, hey, fraction to decimal, okay? And so, pressed the wrong button, didn't I? 2.5 is equivalent to 5 halves. So we have 5 halves, so this whole oxygen set can cancel with 5 halves here. And again, trust the fractions there, but we have 5 halves oxygen can cancel with 5 halves oxygen. Now there's nothing that can cancel out. So again, we add up, we act like this is a addition problem in math, and we add up our equations. So we have 2 carbons that are solids. We look for anything else that's carbon as a solid. We don't have it, so we just write down 2C as a solid. We look, H2 as our next item up here, and H2 as a gas. There's nothing else that's H2 as a gas. We just have H2 as a gas. And then we turn to our products. There's nothing left after we put carbon and hydrogen down, so we turn to our products. And we look here, and the only product that's not crossed out is C2H2. So we write down C2H2 as a gas. Now this is our double check. This equation needs to look exactly like our desired equation. So we have 2 carbons, 2 carbons. We have 1 H2, 1 H2. We have 1 C2H2, 1 C2H2. So our equations match. It's kind of a good thumbs up that we have in this part here. If that is the case, then we just add our delta H's together. And we've already manipulated these things, so we don't need to worry about them. And so all we need to do, we're going to take 1299.6 plus 787.0 plus a negative 285.8, 0.8, not negative 8. And we get a value here. We get a value here of 1,800 kilojoules. Oh, and I noticed a mistake. All right, hey, I didn't bring down that negative sign. This should have been negative 787. So let me try that calculation again. So again, the negative sign needs to come down because we didn't flip that equation, and that's my mistake there. So we have 1299.6 plus negative 787.0 plus negative 285.8. That's better, all right? So 226.1 kilojoules is the amount of heat needed for this reaction to happen. Now, we could also go a little step further, and we could apply endo and exothermic. Remember, positive delta H, it's an endothermic. Negative delta H, it's an exothermic reaction. So just some things to keep in mind as we go through these particular processes. Okay, so again, take your time, make sure your signs come down, make sure you have your cancellations and things like that correct, because as you can see, I made one little mistake, and that made a major difference on our value that we obtained for our equation, okay? So we have here everything that we need to solve our Hess's Law problem. Now let's move on to enthalpies of formation. It's kind of a different topic that we talk about here. Oh, and I just noticed one thing too. Again, miscalculated this. I typed it into my calculator wrong, so you may be wondering how I got that. That should be positive 226.8 kilojoules. Okay, so that's the correct answer here. Again, if we add this together, 1299.6 plus a negative 787.0 plus negative 285.8, 226.8. Okay, so third time's the charm, getting that one done, but that is how we would add that together in this particular problem. Okay, so now we can move to our enthalpy of formation. Okay, so enthalpy can have some different terms. And really here, it's just depending on what state of matter you are in. So if you have an enthalpy change converting liquid to gases, so think boiling water is a good example, that would be your delta H of vaporization. If something's melting, it'd be your delta H of fusion. Or if something is combusting, reacting with that oxygen, it is delta H of combustion. Now, again, these are just terms that should be familiarized with yourself. You may see these pop up, but there's nothing too alarming with this. What we are concerned about in this section here is our enthalpies of formation. Okay, and so our enthalpies of formation have this. It is the enthalpy change that occurs when a compound is formed from its constituent elements. So basically saying, hey, whatever makes up that particular compound, that particular element, we can add some stuff together and go through a calculation. Now, this has a similar format for the symbol, delta H of formation. So it's saying, hey, what makes this particular compound, and specifically, what's that enthalpy change involved in that? Now, these are found via reactions, and so they are actual lab data that is obtained in this particular process, okay? And so when we go through this particular process, we can also add one thing to our enthalpy of formation, and that is a standard enthalpy of change. Now, this right here is called the standard enthalpy of formation, and basically it's just giving parameters to our delta H of formation. So it's saying the delta H of formation under these conditions was found via these numbers at the standard state. Now, you need to memorize these two values as the standard state. Standard state is 1 atmosphere of pressure and 25 degrees Celsius. And you can see here we have some values that we'll talk about here on our particular examples. So we'll keep moving on here, and we will move to our next set of notes. All right, so our next set of notes says, all right, our standard enthalpy of formation, is defined as the enthalpy change for the formation of 1 mole of a compound with all substances in their standard states, okay? 1 mole. I'm going to underline that because that's going to play a role in our particular example. And the other thing that I want to point out here is that these values, the delta H of formation in standard conditions, 25 degrees Celsius and 1 atmosphere, can be found in Appendix C. Okay, and I want to make a couple other points here. Okay, we for this process of standard enthalpy of formation, are only interested in exactly the formation of 1 mole of a substance under interest. Now, the other key point we need to make here is this. We need to say this. The standard enthalpy of formation for the most stable form of an element is 0. All right, so now let's get to a really important point here, and that's how we calculate this. So the delta H of formation, or the standard enthalpy of formation, the change here, is a lot more comprehensive because we can take this symbol here, and I'm just going to write it down and then explain it later. So we have a lot going on here, a lot of math symbols that we need to talk about here. But to find delta H of formation in that standard state, we have to think about a couple of things. This Greek symbol that we have here just stands for sum. Or if you want to think sum as add, that is perfectly fine. Okay? And then we have our N, which is going to be moles of substance. And that's going to be found via the coefficient. And so maybe I'll just put that in parentheses, coefficient. And then we have our products and reactants, okay? And so products here are all products. Our reactants are all reactants. And again, remember I told you early on in this unit that very key thing for thermochemistry is products minus reactants. Well, here it shows up again, and whoop, this is all reactants. Here it shows up again, and it's very pivotal that we remember this. All right, so I don't expect you to go, wow, yeah, I can use that formula until we actually go over an example. And let's do that here while we have the opportunity. Okay, so here is our enthalpy of reaction problem. We're going to use that formula there here in just a second. And it says calculate the standard enthalpy change for the combustion of 1 mole of benzene to carbon dioxide and water. Okay, and so what we have here is this. We have benzene, which is C6H6, and we can't forget about our unit on chemical reactions and what that does. When something is combusted, it has to react with oxygen gas, okay? And the equation said, hey, we want to know, hey, what is our values for delta H, but it produces CO2 and water. Now, we look at this, and one key thing, hopefully you're not overlooking this, is we need to balance the equations. So right now here, we have a couple of things going on. We have 6 carbons, so I'm going to lightly put this, and you'll see why. We have 6 carbons, and so we need 6 carbons over here. Did that, done. Now we need 6 hydrogens, so we put a 3 over here. Again, very lightly, you'll see why. And now I get to my oxygens. I have 6 times 2, which is 12, plus 3, 15. Well, I need whole numbers, right? That's what I've always been doing. And so what I'm going to do is I'm going to double everything. So I'm going to put a coefficient of 12 in front of CO2. I'm going to put a coefficient of 6 in front of H2O. And that means I'm going to need a coefficient of 2 out in front here. Well, that means now I have 12 times 2, so that is 14, or excuse me, how about 24 oxygens plus 6 is 30. So to make 30, I'm going to put a 15 here. I'm going to clean this up a little bit because that looks sloppy. And so here is my balanced chemical equation. Now what I need to do is I need to think about what I just wrote down. Delta H of formation under standard conditions is equal to the sum of the products minus the sum of the reactants. And so we'll get to that here in just a second. And what I'm going to do now is this. I'm going to start out and I'm going to list my products, okay? And my products, we start out here with CO2, and it's really important that we put the state of matter. It's a gas, okay? And so what I'm going to do, what I'm going to need to plug this into this formula here is our standard enthalpy of formation. So in your periodic table packet, if you look at Appendix C, there's 3 pages of these values here. Now it's ordered usually by substance here. The one exception is going to be water, which I'll show you where that's at. But for CO2, remember it's a gas. So we look at CO2, the delta H of formation, that's what we're interested in. CO2 has a value of negative 393.5, and that is kilojoules per mole. So I'm going to write that down. Negative 393.5 kilojoules per mole. All right. Now my other product is H2O as a liquid. And so H2O as a liquid, like I said, found in Appendix C. Now normally you think hydrogen. It's actually under oxygen for our value here, and I'll show you where that is. All right, so you find it under the broad category of oxygen, and notice there's a lot of H2Os here in our value. We have a liquid, so we want to make sure we grab that liquid value, and that liquid value is negative 285.83. And that, again, is in units of kilojoules per mole. Now, on the flip side here, we have our reactants. And I'm going to squeeze this over real tight here because we're going to need some space. And so our reactants, we start out with C6H6 as a liquid. States of matter. And what we do here is this. We go to our Appendix C. We look under carbon because that's the first element listed. And we find C6H6 as a liquid has a value of 49.0 kilojoules per mole. All right, now the other thing, we have O2 as a gas. So we turn to Appendix C, and we are going to find our standard enthalpy of formation for oxygen. Now I should note this by the time I get to it. Oxygen is in its standard state. Remember what we said about O2, which is in its standard state. The enthalpy of formation is 0. So we can put a value of 0 kilojoules per mole. Okay. Now, what we have here, or what we're going to do, is this. The delta H of formation under these standard conditions is going to be equal to this. Watch very closely. We open a bracket to represent this part right here. And we also start with a parenthesis. Now we look in our chemical equation and we start out with our N, our number of moles. So the number of moles of C6H6 is 2. So we have 2 moles of C6H6, okay? Times the value, made a big mistake here. Made a big mistake. It is products minus reactants. We got to halt ourselves, right? So products minus reactants. That's good that we noticed that, and we got to do the order that it's prescribed in. So not C6H6, but our CO2. Okay, so backtrack here. We have 12 moles of CO2 times the value for CO2, which is negative 393.5 kilojoules per mole, and we close that parenthesis. Now, we add, because that epsilon symbol says, hey, add it together, right? So we start out with the number of moles of our other product, 6 moles of H2O, times the value of liquid H2O, which we tabulated, we found as negative 285.83 kilojoules per mole. We close the parenthesis and we close the bracket. Now, we'll get to that here in a second, but I want to do my setup here. This is going to be subtracted from our bracket. Now I can do my reactants. I open up with a set of parentheses, and I now can start with 2 moles of C6H6. So I have 2 moles of C6H6 as a liquid, and I already looked up, hey, what was that value for our standard enthalpy of formation? Well, it's 49.0 kilojoules per mole, okay? Now, close the parenthesis, we add, start out with the number of moles of oxygen, 15 moles of O2 times 0 kilojoules per mole. Close the parenthesis, close the bracket. All right, I'm out of breath. This is a lot of work so far. Now, hold on to yourself because we're going to need to do the calculation correctly, okay? So the calculators, the scientific instrument calculators here, don't have brackets. So we're going to represent brackets with 2, starting out with 2 parentheses. Then we're going to hit 12 times negative 393.5, close 1 parentheses, add, open another set of parentheses, 6 times negative 285.83, close 2 parentheses. So we closed up this whole top bracket. Now we subtract the reactants. So 2 parentheses again, 2 moles times 49 kilojoules, so 49.0. Close it plus 15 times 0. 15 times 0. 2 parentheses to represent the closeout of the parenthesis here and the bracket. And we press enter. All right. Now I'm going to round to our whole number here. And so our standard enthalpy of formation is, in my calculator, negative 6,535. And that is, careful here, it's in kilojoules, but it's for 2 moles of benzene. So I'm going to write that down. Per 2 mole of benzene, C6H6 as a liquid. And that 2 moles comes from our balanced chemical equation. So to get it in our standard enthalpy change for 1 mole, what we need to do to this is as follows. We need to take our value, negative 6,535 kilojoules, and divide it by 2 moles of benzene. That's what we got it from the reaction. And we do this, all right? So negative 6,535 divided by 2. I'm going to round to my whole number here again, and I get a value of negative 3,268. All right, so some people here may not round to the n. So that may affect your last digit in this particular problem. So you may see a 6.7 or a 6.8 here. No big deal. Again, it's just rounding. And when you're dealing with these numbers, it's not the end of the world here. Now this is delta H of formation under those standard conditions, okay? So we went through a lot. Be careful when you do those problems. You saw me, I had to go back and make a mistake, correct a mistake on Hess's Law, and I had to be really careful here to make sure I started with the products, subtracting the reactants from those. So be careful. There's a lot of numbers that get thrown around here. Really take your time and practice doing those calculations. I would suggest trying this in your calculator like I did. If you didn't quite get something in that nature or like that problem, try it again because it's really effective to do it that way. All right, so I hope you have learned a lot. We've thrown a lot at you, again, mathematically with thermochemistry. And as always, I hope you enjoyed this episode. And if you haven't already, make sure you subscribe.